with Avi Sahu, who is an assistant professor, Division of Translational Informatics in the Department of Internal Medicine over at the med school. And I want to highlight yet another person with a computer science background who has moved into another discipline, in this case medicine. And so, Avi.
Thank you. I will try to keep it short because it's the end of the day, and so I didn't do a justice in the sense that I was trying to make the presentation a little bit more interesting, but I came with even boring title for this presentation. So, so my lab is really focused on how we can bring in large language model on the biomedical domain. And on some of the area right now, the large language model is decent enough. I think there are, despite the problem of hallucination, we see a decent performance on the model. So this is the question which I put in on the large language model, and it gives you a reasonable information. Now it's also possible to get some sort of a citation for all of this information that is provided. But if you start, thinking of in biomedical domain, we have things like protein sequence or chemical structure, right? So if you try to give those information to ChatGPT, it starts giving you a gibberish or like almost no information output. So and that's the reason is quite obvious. The model has not been trained to process this sort of info. So this is a protein sequence. The model was never trained to do that, right? Inadvertently, it could have been possible for model to sort of because it has been also trained on published literature to have some input. So from there, it knows that this is a protein sequence, but fundamentally it cannot understand protein sequence. It cannot understand chemical structure. So, in fact, in biomedical hypothesis, there are also sort of implicit information that we are seeking. So, for example, a simple question like, is this drug X is effective for a specific patient? Is this drug X with specific chemical structure X1 is effective for patient with the genome Y1, right? So we are implicitly really asking about the chemical structure as well as the patient genome, right? And then you can also add into the information that if you for a patient, you want to have some clinical information to be included to make that assessment whether the drug is likely to be effective on that patient. Then you have to, there is an implicit information that model needs to have to make that sort of connection. Right? So really, the large language model is not. It has not been trained on this sort of information. It cannot process it. So we have been sort of thinking on it, and so this is a sort of a very simple example what large language model does. For us, it's sort of a next word predictor. It simply predicts the next word, right? So, for example, let's say the input of the model is like Paris is the city. What this model is trying to predict is what would be the word that would come after the city, right? So the way it does is it takes this input, Paris is the city, this 4 word, it converts into this sort of token. So they are sort of numbers which represent unique words. And those tokens are then processed by this large language model. And the output of this large language model is, in the English vocabulary, if let's say there are 30,000 words, it creates the probability that what is the word which is likely given this four word, right? So it is just trying to create the predictor what is the next word. Okay. Now, a naive idea, if you want to sort of include new vocabulary, the new biomedical vocabulary like protein sequence or chemical structure, is to think about current vocabulary of large language model or exact word, and can we sort of include new vocabulary, right? So, for example, these are the vocabulary of compounds which can be represented by smiles, and so the words which are here like C and N have a different meaning than what is currently the model is trained on. So the question is that can we increase that vocabulary? And so people have done those sort of extension. There are models which has sort of increased the vocabulary of current English language to also include the protein sequence or chemical structure. There are certain problems for this. First is that the rules, the structural rules that a protein structure, a protein sequence or compound sequence follows, they are very different than what the grammatical structure of natural language is. Right? So that need to be accommodated. Things like smiles, which is sort of a one form of a compound structure, doesn't really represent a lot of other information that is needed. Like we need a compound structure or protein three-dimensional structure to sort of input to the model so that we can sort of model its function. Right? And then the third thing is, which is the biggest challenge for us, is that it needs very extensive training data, right? And then also a sort of computational power which the academic lab doesn't have. And so to address this issue, a couple of students in the lab, what they came up with is a much simpler solution. Can we use the existing models to sort of increase the vocabulary of the large language model? So what they did was they started with this sort of a small structure, this chemical structure, and then use this encoder. And what this encoder does is that it takes the compound and then sort of creates a numerical representation. What Sarah was showing about in terms of the embeddings. So once you have this embedding space, what this embedding space in general does is that it creates two objects. So in compound, in our case here, if they are similar, then in this numerical space, they should be close to each other. And if these two compounds are really different from each other, then they should be far from each other. Right? So that's what this embedding space does. The challenge with this embedding space here is that this embedding space is a compound numerical space. It's not a word numerical space. So we cannot still process this small structure through large language model. So we came up with much simpler idea that how about we map this compound space to the space of words. Right? So can we transform them? Can we change it so that they can be processed with the large language model? And so we created a simple projector. Gods are in the detail. There are different ways we can model this, but the bottom line is we are sort of mapping two different space, compound space with the word space. And once you have those word space, you can process those the compound directly through the large language model. So you can also add things like instruction to it. You can add question and answer to the compound. And so that could be completely processed with the large language model. Okay. So what is the basic idea here is how we can use current infrastructure. So if you can do so, if you can do this mapping correctly, we can use the existing large language model. We don't have to train it from scratch. In addition to that, there are big labs or even big tech companies that have created encoders which has been trained on the billions of compounds. So we can take advantage of pre-trained model if we can do this mapping correctly, right? So all we need to do is this sort of projector, which is how we can map these two different worlds. So, like what we observed was, as soon as we do that, we can create a model, create a ChatGPT kind of a model, where you can also input smile structure, right? So these are the example which I'm giving, where we don't give the name of the compound, but we give the actual compound structure of, let's say, the carboprost, and we can ask specific question that what this compound have effect on the blood vessel. And the ground truth answer is that it causes a vessel restriction, and then the chem to text, the output, it accurately can sort of predict it, because we have been able to sort of map the compound to the text word. So we can also, ask much more detailed questions. The basic idea is the model is not knowing the name of the compound, but it is using the chemical structure. Okay. Now this model is incredibly flexible. You can now really take the SMILES encoder, which is the compound encoder, you can replace it with an amino acid encoder. And that's what other graduate student in the lab is working on, where we are taking SMILE amino acid encoder and then sort of using this very similar strategy to map amino acid sequence to the text space, and then using the large language. Right. And again, there are many big encoders that has been created. For example, AlphaFold is one such encoder. ESM2 is one such encoder that take amino acid sequence as input, and then you can create an embedding from it. So again, what we are doing here is we are using the existing models to sort of bridge the gap between two different worlds, between amino acid protein sequence and the text. One of the other sort of the project we can also working on a very similar idea, where now we take this sort of chemical encoder, and instead of the chemical encoder we can take medical images. So with Dr. Parashar, Gulshan Parashar from UNM, we are working with the endoscopist. He's a GI division chief. They do a lot of colonoscopy or endoscopy, and one of the things they have observed is there is the interpretation of endoscopy results are so much dependent on the expert. That if you get a right expert, you can avoid a lot of downstream invasive biopsies. So if you can somehow bring in those expert idea during the endoscopy procedure, by that we mean that if you can create a co-pilot which can sort of tell that, okay, given this image or given this video, there are polyps which are likely to be benign, so we don't have to do any biopsy, or we don't have to do the follow-up. So that would sort of save patient with a lot of unnecessary clinical procedure, right? So what we are using a very similar idea, where we have an encoder for endoscopy image, and we sort of map those medical image concept, endoscopy images, to the text through this projector. And then once you have this mapping, you can directly use the off-the-shelf large language model to answer a specific question. You can ask, for example, describe this image to the model, and it gives right now at the level of medical student, what it can describe what the image which we are processing. Right? You can also use it at more expert level where you can ask much more detailed follow-up question. Basically, for a given image, you can ask any free form of the question, and if the model has been trained on those sort of questions, it would be able to reply it quite accurately. So we are right now working on sort of improving this model and then making it sort of deployable in the real-time surgery process. So what I want to end this presentation is that although this framework is really very flexible, you can integrate any sort of signal. For example, you can add EEG by replacing the chemical encoder with the EEG encoder. There are specific challenges. So I will leave you with those, some of those thought process. So what happens if we, instead of having just a text decoder, we also have a protein decoder, where the model can also not only output the text, give you answer yes and no, or give you a follow-up question, but it can actually output a specific protein sequence. And what if some nefarious actor gives the current variant of COVID and asks, can you create a more infectious version of this COVID virus? Or can you make it resistant to specific vaccine? So that's the thing I want to sort of end the talk with. So despite all these challenges, we are also excited with the promise of this technology because of its incredible flexibility in applying this technology on various biomedical domains. Thank you. I'm happy to take questions.
Can we go back to the last question? So, it comes in as a protein sequence, and then the protein decoder outputs the protein sequence. Are those supposed to not in this diagram?
Yeah, so you can actually give both protein sequence and text as an input, and it can give you protein sequence and text as an output. So,
but are those the same protein sequences?
It doesn't need to be same protein sequence. You can ask the model that, this is my initial sequence and I want to modify it for my specific purpose. Now you can use it for good purpose. You can take it, specific compound, and sort of say that, can you make it so that the side effect is reduced while keeping the efficacy of this drug same? But you can use it also for more nefarious purposes.
Really interesting work, thank you, Avi. Just a quick comment on medical images. One of the things that ends up happening oftentimes when the human being is looking at an imagery, okay, we tend to focus on something that's very glaring. Brain focuses on that, okay? So in the context, for example, of endoscopies, one of the things that would be very important is to capture the entire image process. Okay, so what happens when an individual is looking at an image, she or he trains on that and misses other things. So you go in for a follow-up that appears to be something new. It's not. It was a glaring signal that took all of the human attention, essentially, no matter how well trained someone is, and other things are mixed. So one step is what you're doing, but another step is to put that in the context of the entire data feed of all the imagery to capture things that are normally lost by the human.
Yeah, so definitely, I think, this things like endoscopy is really interesting because of its real-time nature, right? So you, even if model is making error, because there is endoscopist and he or she can ask, okay, let me change the angle of this endoscope and see this area of concern through other angle and see what the model output is. It could be incredibly powerful. At the same time, we can sort of capture those interactions and then improve the next version of the model. So that's another sort of super interesting idea which comes by some of this procedure is to be sort of interactive, where you have sort of if some non-expert is doing this procedure, and if we sort of say the warning that there is this serrated polyps which may be not benign, then he or she can ask more superior person and come and review it, right? So really the real-time advantage in the medical procedure sort of gives another dimension by which not only you can improve the model, but also sort of, increase the accuracy of the model by looking at different angles and sort of bringing in more information into the thing.
So I assume that when you get the output for the protein decoder or any other off-color diagnostic, you use a beam search, right? And what you showed us is an output that has different magnitudes. And so in the beam search, you have different sequences with different likelihoods.
Yes.
And so I wonder whether this or other strategies can be used to quantify the uncertainty of your response, which I believe is very important, for example, in medical applications. So in a way, we will be able to quantify the risk of taking a decision. Is there any approach in this direction?
Yeah, so uncertainty quantification is definitely possible, at least, for example, when you have a multiple, let's say, input. So specifically endoscopic procedure, you don't have to rely just on one image, you have multiple images. And then sort of you can look at the variability, how does the variability change, and you can sort of, so there are natural way to sort of estimate uncertainty. But there are also sort of, even if it's a static images or static output like smiles, compound structure, there are approaches by which you can sort of estimate the uncertainty. Right? The other thing is that you can ask very specific questions. So you can ask, can you change this carboxyl group to something else so that it's more efficacious, right? Or you can do a follow-up question that given this output, this looks like it's a hydrophobic residue. Can you make it hydrophilic? So that really is sort of a key to have this sort of interactiveness with the system that would make the system more powerful than what it should be.
Excellent. All right. We are once again going to have to cut questions there, but thank you again, Avi, for a fascinating and slightly scary at the end presentation.